using essentially Fourier transform, right? So take the circular matrix, map it to that sum over there, right? Each of this omega is a root, nth root of unity. So that generates a primitive n root of unity. So generates your cyclic group, right? I should have used multiplicative notation. So in your mind, replace z quotient nz by cn. Okay. Now the thing is, you can show, right? Now I can multiply this to inside this group algebra, and you can count the number of multiplication is exactly n. Okay. When I say multiplication, I mean really multiplication, right? If I take x multiplied by y, this is multiplication. If I take 5 multiplied by y, this is not a multiplication. This is scalar multiplication, right? In bilinear complexity, you only count multiplication, okay? And because of that, all these maps are actually free. So the point is, well, okay, the point here is this is actually the simplest case, okay? This is in fact an isomorphism. The I here and the pi here, these are isomorphism, okay? The circular matrices and Cn, right, with coordinate entry-wise multiplication, and the group algebra of the cyclic group with n elements, these are all isomorphic as algebra. So this is actually the sort of the simplest example. Okay? Now, in this case, you can show that the rank of taking a circular matrix multiplied to a vector is exactly n, meaning you can do this with exactly n multiplication. Okay, now the thing is, what about Toeplitz and Hankel? I'm going to build it on top of that. I don't have to, but since I already have the circular result.
So do you get the border also by the same argument?
Yeah, the border, essentially it's a very simple argument, right? Whenever you have the vector spaces, let's say u, v, and w, right? U tensor, v tensor, w. And the thing is, if the rank, right, if your image, the beta uv, if this is surjective, then the rank has to be the dimension of w. Okay, that's how you get it. And the border rank has to be the same too. So this is actually quite easy to show, right? And this is exactly n because Cn has dimension n. Okay? And likewise here, this is how I'm going to get 2n minus 1 and 2n minus 1 over there because my space of Toeplitz matrix has dimension 2n minus 1. And the map is surjected, the bilinear map is surjected, and that's why it has dimension 2n minus 1. This is far easier than doing like matrix product. Okay? Now the thing is, how do I do this for Toeplitz? Well, I'm going to build on my previous result, but this is going to be something that Jian-Lin knows very well. Every Toeplitz matrix can be written as, every n by n Toeplitz matrix can be written as the top left block of a 2n by 2n circular matrix, okay? So I just need to choose so every time I have Toeplitz matrix Tn, I can write it in a 2 by 2 block matrix. I just need to choose my Sn appropriately. And then this is going to become a circular matrix of dimension 2n by 2n. So Toeplitz matrices can be embedded in the algebra of 2n by 2n circular matrices. Okay? Now this is exactly the embedding that I'm looking for because I'm embedding things into an algebra. And then I can use this to do the multiplication, do the algorithm that I showed you on the previous page, right? And then this is going to give me an algorithm that actually accomplishes a Toeplitz matrix vector multiply in 2n minus 1 multiplication. Okay? It achieves the optimal bilinear complexity. You can also show that the rank is exactly 2n minus 1. You cannot do better than 2n minus 1, which is intuitive because, right, a Toeplitz matrix is defined by 2n minus 1 parameters. Right? It has n square entries, but it only has 2n minus 1 parameters. So 2n minus 1 is the best that you can hope for, and in fact, this achieves that. Okay? What about Hankel? Hankel, you're going to take advantage of the fact that there is a linear isomorphism. Right? Take a Hankel matrix, multiply it by this permutation matrix. This takes the first row, bring it to the last row, and so on and so forth. This flips the matrix around, right, in some sense, the reverse identity matrix. This, if H is Hankel, then this matrix multiplied by H is going to be a Toeplitz matrix. Okay? So this is a isomorphism, right? And in some sense, you show that Hankel matrices are isomorphic to Toeplitz matrices using this isomorphism. And Toeplitz matrices can be embedded in 2n by 2n circular matrices. And then using this, you get what you need. Okay? You get the algorithm that you need. But I should say that this result is not new. This beta, at least this one here, this was in Dario Vini's and Capovani's. They got it using another approach. I'm not using the approach that I described here. But the Hankel result, is sort of trivial, and the circular result that sort of is new. But these are not really very difficult. How about what is completely new? I don't think anybody has ever discussed this. It's actually for symmetric matrix. How will you do this for symmetric matrices? Okay. right, how do I take advantage of the fact that a matrix is symmetric when I perform a matrix vector multiply, right? A symmetric matrix has n times n plus 1 over 2 elements, right, entries, right, distinct entries, and I multiply to a vector. The best I can hope for is that I just need exactly the number of parameters in a symmetric matrix, which is n plus 1, n times n plus 1 over 2. And that, in fact, can be done. How you do it is not obvious, okay? Well, first of all, you observe that a 2 by 2 symmetric matrix is Hankel matrix. A 3 by 3 symmetric matrix is not Hankel, but you can write it as a sum of 2 Hankel matrix, right? This first one is Hankel, the second one is a Hankel matrix, the 1 by 1 Hankel matrix bordered by 0. What about a 4 by 4? You can write it as a Hankel matrix plus a 2 by 2 Hankel matrix bordered by 0, plus a 1 by 1 Hankel matrix bordered by 0. And this you can do for however, whatever, this generalizes to any n by n symmetric matrix. So the algorithm for multiplying symmetric matrix to a vector is to first decompose a symmetric matrix into a sum of Hankel matrices, okay? So the thing is, you can also construct that homomorphism, right? It's going to be embedded into a direct sum of spaces of Hankel matrices, which is in turn going to be embedded into a 2n by 2n circular matrix, and you're going to do the operation in there and amend back, okay? And all this are optimal in both the approximate sense and the exact sense, okay? Rank and border rank. What about multi-levels? Okay? Well, the thing is, we're going to use tensor product in a different way. When you take tensor product of operators, well, it's often called Kronecker product. So this boils down to the observation that when I have BTTB, like a block Toeplitz matrix whose blocks are all Toeplitz, is simply the Kronecker product of the spaces of two vector spaces of Toeplitz matrices. What about a 3-level one, right? A BTTB matrix whose blocks are Toeplitz, or a Toeplitz matrix whose blocks are BTTB, right, equivalently. That's the Kronecker product of 3 spaces of our Toeplitz matrices. Okay? Now I'm going to take advantage of this, and then using this, right, and using the algorithms that we have on the previous page, and using this very simple result that we showed, that when you have Kronecker products of vector spaces of matrices, right, vector subspaces of matrices, the rank that you get out of the structure constants is multiplicative. Okay? Okay?
And the border rank?
And the border rank is the same. It has exactly the same feature. Okay? No, that is one condition. Sorry, I missed out that condition. There is one condition that has to be satisfied before I can write this. Okay, I missed that. Sorry, and I cannot remember it offhand. Okay, but in this case, for the kind of matrices, spaces of matrices I'm interested in, they are satisfied. Okay, so in particular, what is the tensor rank, or what is the bilinear complexity of BTTB matrix multiplied by a vector, is 2n minus 1 times 2n minus 1. Right? Okay, for this kind of matrices, and it extends to arbitrary number of levels, right? Because this result extends to an arbitrary number of levels with that condition I cannot remember satisfied. Okay. Now I don't have time to discuss other things, but the technique that I discussed applies to almost any structured matrices that you're interested in, as long as they form a subspace of the space of all matrices. Okay. Okay. So for instance, it doesn't work for instance Van der Waals matrices. Okay. Because Van der Waals matrices doesn't form a subspace. You take the sum of 2 Van der Waals matrices, it's not a Van der Waals matrix. But as long as it has a property that you take the sum of 2 structured matrices, it gives you the same structure, it applies to that. Okay? So like you take a sum of Toeplitz and a sum of Hankel, right? Hankel plus Toeplitz, that is not a Toeplitz, not a Hankel, but it forms a subspace of its own. Okay? It's the space of all Toeplitz plus Hankel matrices, and it applies in that context too. Okay? So, so it applies in actually a wide variety of contexts. We can discuss other operations, and we do, right? Commutators, matrix product. We can take simultaneous matrix product. What do I mean by that? I have a matrix A, I have a matrix B, a square matrix B. I want to simultaneously form AB and AB transpose. Okay, simultaneously form AB and AB transpose. How can I do that quick? Right? It applies to those kind of situations too. And remember that my technique essentially boils down to embedding objects, matrices and vectors into algebras. Right? Where do the algebras come from? I show you group algebra, right? I show you essentially, I only show you group algebra, but you can talk about other, like for instance, if I talk about triangular Toeplitz matrix, I have to use like coordinate rings of schemes, right? Or cohomology rings of manifolds. So this is going to potentially give you insights. We didn't really exploit this. We just realized that the algebra that we use is actually a cohomology ring of CP2, right? And you can have more general type of algebras like PI algebras, meaning that you take free algebra quotient of with an ideal generated by whatever relations that you want. Okay, and so this kind of stuff. So in some sense, right, this is a gadget for you to find tensor decomposition of your structure tensor using algebra, using properties of the algebra that you know. For instance, if that algebra comes from algebraic geometry, right, or comes from algebraic topology, there are ideas that you can, insights that you can exploit because they arise from those venues. Okay, and if you're interested, the main paper is this one, which is going to appear in FOCM, fast structure matrix computations, and it doesn't have the pseudocode, right? If you want to act, as I said, this appears to be an abstract thing, but at the end of it, you have actual pseudocode for all these algorithms. Okay, where are those algorithms? It's in this Proceedings of Algebraic Information Theory. You can find the algorithms for almost everything that I mentioned today. Right? The actual algorithm, sort of MATLAB-ready algorithms that you can use. Okay, so that's all I have for today. Thank you very much.
So are there any questions?
Yeah, so the metric you used for a lot of this was bilinear complexity, which I wasn't familiar with before this talk, but it makes a lot of sense in this context.
Yeah.
But I'm curious, I'm really impressed with like the bilinear complexity for Toeplitz. If with other metrics like floating point operations or runtime, do you still get linear, or is it some other kind of scale?
So the thing is, let me say this, right? So as I said earlier, what I'm counting here is bilinear complexity, right? Bilinear complexity means I only count multiplications, right? Discount additions, right? For instance, Gauss method is going to have many more additions than, let me see, right? So for instance, Strasson's method, right? If you use Strasson's method, you save one multiplication, but you pay the price by having a lot more additions. Why don't I count everything? Why don't I count like addition and multiplication, right? Which includes subtraction. Well, the thing is that this is sort of one of the biggest open problem in computer science. Okay, let's say I'm interested in complexity, total arithmetic complexity, even like simple things like FFT. Okay, FFT. What is the complexity of FFT? It's sort of upper bounded by n log n. Is that optimal? Nobody knows. It's one of the biggest open problems in computer science. So if I am interested in total arithmetic complexity, immediately I run into this obstacle. Whereas if I'm interested in just bilinear complexity, suddenly all this goes away. What is the bilinear complexity of FFT? It's 1, okay? It's O1. FFT can be done in constant time when viewed from bilinear complexity. So a lot of these problems get swept under the rug. It reduces to just like, what I really need. Because if you think about it, like things like FFT, you can implement in hardware, right? What you really need to change is like AB, things like this. You need to, these are the quantities that change, right? Your A1, A2, A3, A4, B1, B2, B3. These are the things that change. Other stuff, like, all those constants in front, and those you can implement in hardware. So what you really need to control are like so bilinear complexity is sort of very relevant in this way. You're only interested in things that can change, that you cannot implement in hardware. Things that you can implement in hardware, you actually don't care so much. Yeah?
That makes a lot of sense. Thank you.
Okay.
So the BTTB case you mentioned,
Yeah.
is that one, just a special case where you have the chronicle product?
No, it's always the case. Whenever you have BTTB, it's even more general than that. Okay. So for instance, let's say I have BTHB. Okay. Block Toeplitz, but the blocks are Hankel. Okay. Now how do you do that? It's very simple. You take the first space is Toeplitz, the second space is Hankel, then you get that.
So you have the chronicle product form. That means the plots on different diagonals are actually related.
Of course, right? Yeah, but that's what I mean by BTTB, right? Because it has to be a block Toeplitz, right? Which means that the blocks on the diagonal must be constant.
Along different diagonals.
Yeah, along different diagonals they change.
They're also related. But
they're not related.
They don't have the chronicle product form.
No. Anytime you have the BTTB matrix, you can write it as the chronicle product of two Toeplitz. That you can be sure of. Yeah. But the thing is, So, and I should say that this also holds for something that's way more complicated. Like like I mentioned this BHT, right? BTHTHB, right? Block Toeplitz-plus-Hankel, Toeplitz-plus-Hankel, and it comes out, right? You know this, right? Block. This comes out in applications. There are people interested in image processing who actually have to deal with this kind of matrices, and it applies to this, right? You take Toeplitz-plus-Hankel matrices, that is a subspace, and you take the chronicle product of two of those subspaces, and the technique I described gives you the optimal algorithm for multiplying that to vectors.
Okay, I think we are out of time, so any other questions can be done offline. As I said, we are going for